Good morning, everyone. I'm Marco Pradelli, and the title of my research is Innovative Techniques and Methodologies for Embedded System Safety and Liveness. My research of this year is focused on the development of Part-Whole Statecharts and is the prosecution of the activity of the first year. I will present results that concern time management in Part-Whole Statecharts, fault management, and an application of this formalism to a case of study that involves a dialysis machine. And I will conclude with the foreseen research for this year of doctorate. So, time management regards the representation of timing constraints in Part-Whole Statecharts. Timing constraints are very common in embedded applications. So there is the need to implement something that allows to manage these constraints. The first solution that I found are the timed states that can be seen as special states with only a time constraint. Another step of development of these timed states is the embedding of the timers in a state to avoid the modeler to design a model for each timer that is used in the application. Finally, a timed state can represent the condition where a command is sent to a physical device and the controller is waiting to see the feedback of that action in the real world. This approach allowed me to develop a pattern that can be applied to physically connected actuators and sensors. For example, here we have a pump and a flow controller that is placed on the pipe after the pump. And below is an example of a controller for these two devices. S state can represent the condition where the pump is off and the controller is saying that no fluid is circulating. Then if I send a command to start the pump, in some cases I didn't see a feedback, instantaneous feedback, because, for example, I have to reach a night pressure before the flow can start. In this way, I can wait in that timed state for the feedback or the timeout. If the timeout is the first one that arrives to the controller, I go to a particular state where I can manage this problem. This pattern allows or helps to produce a self-contained components where you can see the normal behavior is mixed with the fault-tolerant behavior. And this is the first step to introduce the fault tolerance in Part-Whole Statecharts. This is a bigger example with pump and pump controller and the whole controller. This is a fault-tolerant module that allows to command the devices and to perform some fail-safe operation. This has been developed for a case of study where you have 4 pumps that must be used on the basis of what pumps are available. This result is possible because Part-Whole Statecharts allow the user to explicit the behavior of the controller in that section that is called the whole section. The model can be validated in the modeling phase, not with techniques a posteriori, of course the time management and the modularity of this approach. Another development concerns the macro-states. A macro-state is a state that contains a state machine. This is not a new thing because, for example, Statechart did it many years ago. But in Part-Whole Statechart, I use state constraints. So the embedded state machine must always respect the external constraints. This can be validated in two ways. The embedded machine can see only the components that are not involved in the external constraint, but is a very rigid approach, or each constraint must be checked for the inclusion in the external constraint. That means that C2 and C3 must be contained in C1. And this guarantees the containment of the behavior of this machine in the parent constraints. For that concern practical application, I am developing a software tool that is now able to design and validate models of part-whole statecharts, and the state machine embedded in macro-state, that is what I just said. And an important feature is the ability to provide a log of the validation process. This is important in some embedded fields because, for example, in aeronautic application, before to use a software, the developer must provide a proof of correctness of that software. This is an interesting first step in this direction. Finally, this tool, by means of the validation at the modeling time, is able to use a graphical convention to show to the user inconsistency in the model that can be unsatisfied constraints or disconnected constraints, and for that concern transition, unfeasible or incompatible transition, incompatible with the semantics of the state, of course. I applied the part-whole statechart formalism to a case of study. I used a dialysis machine because dialysis treatment involves the patient blood. For this reason, is full of safety constraints, because if the machine stops working or lose some blood or other faults, the patient's health is easily damaged. So this is a good example to test the validity of the strengths of part-whole statecharts. The resulting model is a modular model, hierarchical modular model. This is the layout of the produced blocks. And the advantage of using part-whole statechart to model this case of study are in the increased modularity. Each box is a physical device, for example, sensors, and rounded boxes are a module that at the inside they have other components. For example, this is the watchdog that checks for the safety properties, and this module involves all these components. Each module is isolated. That means that the behavior is contained in the module. So this results in increased usability, in a better understandability, thanks also to the hierarchical approach. And for that concern validation, the module has been validated and the log is available. And of course, I used the software tool to do all these things. Future work on the part-whole statechart developments will regard the time management in hierarchical part-whole statecharts and how timing constraints are spread on different levels of part-whole statecharts, a complexity analysis of the validation algorithms. I have a few data, but I just started this task, so it's too early to present results. The application extended part-whole statechart, I mean with the future work, to a case of study or a real application, I hope. The development of software tool will be carried on, and I will investigate the how and if implement some code generation facilities, because it's the next step to produce the software to be executed on a microcontroller on the field. So I've concluded. This is a list of my publication. The technical report is under revised and will be soon available on the site. And I also have one submission. I've concluded. If there are questions.
Marco, I have some questions. I see that your work after 2 years is not exactly concluded, but is in a very stable situation. So now I have two things to ask you. The first one is about the interface. Have you an interface for designing the state chart and the time? Did you develop this part? The second one instead is if you have just planned a real application where to try to apply this, maybe in collaboration with some companies.
Okay, first question, yes, I have an interface that is the software tool that allow to design and validate the models, and that software used to validate all these modules. And for that concern the second questions, I have not a contact with a corporation, but this is what I can do. I choose the case of study, I collected specification, and I applied the method to those specifications. This is almost complete case of study, and is based on the specification that I can collect. This is what I can do for now.